Okay, this is the Chapter 10 practice test walkthrough video. Just remember, on this test, the most important thing is knowing how to set up the problem you're being asked. After that, you got to get it in your calculator correctly, and you should be good to go. But knowing which conversion factors to use, in which order, that's the biggest part of this test. If you can do that, you'll be in great shape. So first, things that you should make sure you have on your note card, and you probably want to pause this in a minute to have time to take a look at this and write it down. You need to be able to do mole to particle or particle to mole conversions, molar mass of elements and compounds using the periodic table, mole to mass, mass to mole, and then mass to particles and particles to mass. And for honors, you need to be able to do volume to mole and mole to volume, and also volume to mass and volume to particles. So those are all using the molar volume of a gas that we talked about at the end of the chapter. You need to be able to figure out the percent composition and be able to calculate the empirical and molecular formulas if you're given the percent composition. So pause here if you need to write that down, and then continue on. On the test, you will, in honors, be given a periodic table. You will not, however, be given the conversion factors like 1 mole equals 6.02 times 10 to the 23rd, or 1 mole equals 22.4 liters for a gas at STP. So you need to know those by either writing them on your note card or memorizing them. Alright, so on to the questions. Combustion of propane gas with oxygen produces carbon dioxide and water vapor. What is the molecular mass of propane? Well, if you didn't already know what propane was, which is C3H8, you should hopefully have been able to do that by process of elimination, because all the other things, so oxygen, carbon dioxide, and water, are all mentioned, so you should know that that's C3H8. To find this, you have 3 carbons and 8 hydrogens. So we take the mass of carbon, look on the periodic table, you'll see the mass of carbon is 12, multiplied by 3, and that's 36. And then hydrogen, the mass of hydrogen is 1, and there are 8 of them in that molecule, so that contributes 8. So altogether you have a mass of 44 grams, which is choice A. Balloon contains 3.1 times 10 to the 22nd molecules of oxygen. How many moles? Okay, so this is molecules to moles. So in order to do that, we take the number of molecules that you're given over 1, and we're converting to moles, so moles needs to be on the top. The number of molecules in 1 mole is on the bottom, 6.02 times 10 to the 23rd. So then we end up dividing 3.1 times 10 to the 22nd by 6.02 times 10 to the 23rd. And when you do that out, you're going to find that it's 0.051 rounded, okay, which is answer choice B. When you're doing these, remember to use, for scientific notation, use the second E function. Okay, so you would enter this into your calculator as 3.1 second E 22. You don't need times 10. That'll keep all your scientific notation in order in your calculator so that you get the right answers for these problems. So 3.1 second E 22 is all you need to enter, and then divided by 6.02 second E 23, and that would take care of it. What is the mass of 1 mole of liquid water? Well, water has a formula of H2O. The fact that it's liquid doesn't really matter. It would be the same whether it was liquid, solid, or gas. But to find the molar mass, you take the mass of hydrogen from the periodic table, which is 1, and multiply it by 2 because there's 2 of them. So that's a contribution of 2. Oxygen has a mass of 16. There's only 1 of them, so that's 16. So your total mass is 18 grams, which again is choice B for this one. How many atoms are there in the 32 gram sample of carbon? So we're going from grams to atoms. There is no direct conversion because every atom has a different mass. So we can't go straight from atoms to grams, but we can go from grams to moles, and we can go from moles to atoms. So anytime in these types of problems that you do not have moles either as the start point or the end point, you're going to need moles as a middle step. Okay, so just keep that in mind. If moles is not in the question, you're going to have to do a two-step problem, at least. All right, so going from grams to moles is just taking the number of moles given, 32, and dividing it by the molar mass of the element or compound. In this case, it's carbon, has a molar mass of 12 grams per 1 mole. So you do out 32 divided by 12, and you get 2.67 moles. And then now we've done grams to moles, so we want to do moles to atoms. Well, 1 mole is equal to 6.02 second E 23 times 10 to the 23rd. Multiply that out, and you get 1.61 times 10 to the 24th. And it might say on your calculator 1.61 E24, which means times 10 to the 24th. So that's choice C, the multiple choice. Okay, moving on to the problems. A lot of these are going to be the same type of thing we just did in the multiple choice, but they're not multiple choice. So make sure you show your work and circle your final answer. So we're going from moles to atoms of sodium. 6.73 moles, and we're converting to atoms, so we know 1 mole of atoms is 6.02 times 10 to the 23rd, so you punch in 6.73 times 6.02 second E 23, and you get 4.05 times 10 to the 24th atoms. Okay, if you did that in your calculator and you got some other number, for especially with an exponent, different exponent, you may have done it in the calculator wrong, so make sure you use the second EE function. Okay, we are going from molecules to moles. This is the reverse of what we did in the last problem. We're starting with molecules, which would be the same as starting with atoms or anything else, particles, whatever you want to call them. And we're converting to a certain number of moles. Well, 1 mole is 6.02 times 10 to the 23rd. And if we multiply that out, so you do 4.26 second E25 divided by 6.02 second E23, and you get 70.8 moles. If you get something like 7.08 times 10 to the 59th or something like that, then you multiplied instead of divided, or you put it in your calculator out of order. We're going from moles of water to molecules. So this is just like the first problem we did. We've got a certain number of moles. This time it's less than 1 mole. All right, so we're going to have the number of molecules is going to be less than 6.02 times 10 to the 23rd, because we don't even have a mole. So we do 0.0324 times 6.02 second E23 in your calculator equals 1.95 times 10 to the 22nd. Or again, in your calculator, it would see 1.95 E22. So there's your answer there. And that is molecules, just to be sure we get the units in there. 4.27 moles of nitrogen to grams. So now we're doing molar mass problems here. We've got 4.27 moles. And 1 mole of nitrogen, look it up on the periodic table. Nitrogen has a molar mass of 14 grams. So we just have to do 4.27 times 14, which is 59.8 grams of nitrogen. Done. Convert 54.9 grams to moles. So this is going in the reverse order. And so we're going to do 54.9 grams and 1 mole of SO2. So we have to look up sulfur is 32 grams, oxygen is 16 grams, but there are 2 of them because it's SO2, so that's another 32 grams. So the total here is 64 grams for SO2, 64 grams per mole. So 54.9 divided by 64 is 0.858 moles. All right, convert 1 mole of aluminum oxide to grams. So it's moles to mass again, moles to grams. So we're going to need to figure out the molar mass of aluminum oxide. Well, it's Al, which is a mass of 27 times 2, 54. And it's oxygen, which is 16 times 3, for a mass of 48. So the total mass you've got here is 102 grams per mole of the whole compound. Now I've got 1.57 moles. So if 1 mole is 102, then 1.57 moles will be 102 times 1.57. Do that out, and you get 160 grams. That's rounded to 3 sig figs. Convert molecules to moles of oxygen at STP. The STP thing doesn't really matter here because we're just doing moles to molecules or molecules to moles. But it's 3.803 times 10 to the 25th. 1 mole is always 6.02 times 10 to the 23rd. Molecules, atoms, particles, whatever you have. So 3.803 second E25 divided by 6.02 second E23, and you get 63.2 moles. Remember, if your answer is in moles or grams, your answer should be a relatively small number, like on the order of tens or hundreds, or a small decimal. If your answer is in molecules or atoms, it should be something like this, where you've got a big exponent of 10 out there. If you are doing moles and you get an answer like this, you've got something that's backwards in your calculator. If you're doing molecules and you get an answer like this, again, you've either divided when you should have multiplied or the other way around. So just a sort of logic check on these problems to make sure answers are even reasonable. All right, converting molecules to grams. Here's another one where I don't have a direct conversion from molecules to grams. Moles is not my start point or my end point, which means moles has to be in the middle. So I go from molecules to moles and moles to grams. So molecules to moles, 6.37 times 10 to the 25th molecules, and 1 mole of molecules is 6.02 times 10 to the 23rd. That's the 23rd. In your calculator, you do that out, and you get 105.8 moles. And then we go from moles to grams. For CO2, you've got a carbon, which is 12, and you've got 2 oxygens, which is 32, so a total of 44 grams for CO2. 44 grams is equal to 1 mole. So we do 105.8 times 44, and we come up with a number 4,660. So you can't have numbers in the thousands or hundreds with grams and moles, but it shouldn't be, on the order of 10 to the 25th or even 10 to the 15th or anything like that. Convert 65.5 grams of argon to atoms. Okay, so this is the reverse of the last problem, but we don't have moles, so we need to go to moles in between. That's our middle step. So 65.5 grams of argon, 1 mole of argon, if you look it up on the periodic table, has a mass of 40. So 65.5 divided by 40 is 1.6375 moles. And I'm rounding a little differently here. I'm not going to round till the end. All right, and then we go from moles to atoms by multiplying times 6.02 times 10 to the 23rd. Atoms is 1 mole. Multiply that out, and you get 9.86 times 10 to the 23rd atoms. All right, we're going from grams to molecules. So again, we got to go through moles. All the conversions have to go through moles at some point. So 120 grams of water. Okay, the molar mass, or sorry, chlorine. It says water there, get rid of that. It's a typo. So chlorine one chlorine atom has a molar mass of 35.5, so we're going to multiply that by 2. So Cl2 has a molar mass of 71. So we're going to do 120 divided by 71, which is going to equal 1.69 moles. And then to go from moles to molecules, we do 1.69 times 6.02 times 10 to the 23rd. And we come up with 1.02 times 10 to the 24th molecules. Okay, so the next one, this is where we're doing molar volume. So you need to remember that 1 mole of gas at STP equals 22.4 liters. So we're going from liters to grams. So we're not going, we don't have moles, so we're going to have to go to moles in the middle. So 3.53 times 10 to the 3rd liters, and 1 mole equals 22.4 liters, because it says it's at STP, so we can use that number, is equal to 157.589 moles, and a mole of neon, if you look it up on the periodic table, has a mass of 20 grams. So we do 157.589 times 20, and that comes out to 3,150 grams of neon. And we're going now from molecules to liters. We don't have moles, so we got to go through moles to get there. So 7.26 times 10 to the 25th molecules. 1 mole is always 6.02 times 10 to the 23rd. We divide 7.26 second E25 divided by 6.02 second E23, and we get 120.598 moles. 120.598 moles times, it says STP, so we can use 22.4 liters is 1 mole, and that gives us 2.7 times 10 to the 3rd liters. Okay, so there's your answer there. All right, percent composition problem. So percent composition, first step, pretty simple. Convert, first of all, actually, sorry, first find the mass contribution of each element to the compound. Well, the NH4 is in parentheses with a 3, so I have to multiply all those by 3. So nitrogen times 3, 14 times 3, which is 42. That's its contribution. And then hydrogen, it's H4, and then times 3, so it's hydrogen times 12. That is 12, because hydrogen has a mass of 1. Phosphorus, there's only one of them, and phosphorus has a mass of 31 grams, so that's its contribution. And then oxygen times 4. Oxygen has a mass of 16 times 4 is 64 grams. Now if I add all those up, I would find that the total for the compound is 149 grams. So that's the total. These are the parts over here. Step 2. Divide each element by the mass of the compound and multiply by 100. Divided by 149 times 100. Divided by 149 times 100. Divided by 149 times 100. Okay, so we do that out. That'll give us our percentages. For nitrogen, it is 28.2%. For hydrogen is 8.05%. 20.8% for phosphorus, and the oxygen makes up the rest, which is 43.0%. So there is your answers. Always want to just double check, make sure those add up to 100. In this case, they add up to 100.05%. So that is close enough to 100 that we're going to say we got that right. All right, empirical formula. Okay, so step 1 in the empirical formula is to convert the percentages in the problem into grams. So 78.3 grams carbon, 8.7 grams hydrogen, 17.5 grams nitrogen. Step 2, convert each of those to moles. So divide by the molar mass, which is 12. For carbon, 1 gram for hydrogen, and 14 grams for nitrogen, which gives us 6.15 moles of carbon, 8.7 moles hydrogen, and 1.25 moles of nitrogen. Step 3, take all of the answers from step 2 and divide them by the smallest number, which was 1.25. That gives us for carbon, it gives us 4.92. For hydrogen, it gives us 6.96. And of course, for nitrogen, dividing by itself gives you 1. Okay, these numbers for carbon and hydrogen are close enough that we are going to say this is a 5, this is a 7. Step 4 is use those numbers to form an empirical formula, C5H7N. There's your empirical formula. That's the answer to this problem. Okay, compound is found to have a percent composition of 10.01, etc., etc. So this time we need the empirical and molecular formulas. They gave us the molar mass. All right, so first thing we have to do is find the empirical formula. So just same steps as the last problem, and then we have to add on a little bit to get to the molecular formula at the end. So 10.01 grams carbon, 0.84 grams hydrogen, and 89.12 grams chlorine. Okay, step 2, convert to moles. 12 grams for carbon, 1 gram for hydrogen, 35.5 grams for chlorine, which gives us 0.833 for carbon, 0.84 for hydrogen, and 2.51 for, and that's moles, for each of those elements. Step 3, take those numbers, divide them all by the smallest one. Carbon and hydrogen basically came out to the same number, but carbon is slightly smaller, so we're going to use that one. 0.833, which gives us 1, and gives us 3 for the chlorine. So those numbers become the numbers in our empirical formula, which is CHCl3. That's your empirical formula. That's the first half of the question. The second half asks you to find the molecular formula. To do that, we need to do an extra step. Okay, that's step 4, so this is going to be step 5. Step 5 is divide the molar mass, which you're given, 119.37, by the empirical mass. So let's look at the empirical formula. It is carbon plus hydrogen plus 3 chlorines. Carbon has a mass of 12, hydrogen has a mass of 1. 3 chlorines would give you a mass of 106.5. Add those together and you get 119.5. Well, as you can see, that's basically dividing a number by itself. So the answer to that division is 1. And then the next step, step 6, would be to multiply all the subscripts in the empirical formula by the number you get from step 5. In this case, it's just 1. So the empirical is CHCl3, and the molecular is also CHCl3. They are the same formula. Okay, so that's your answer there. Okay, oldies but goodies. Ammonium phosphate. Ammonium is NH4 with a +3. Phosphate is PO4 with a -3. NH4 plus 1, PO4 minus 3. So to get those charges to work out, you need 3 ammoniums to cancel out 1 phosphate. So I put ammonium in parentheses with a 3, and then I slap on phosphate, and that's the formula. Balance the following equation. Well, on the left-hand side, we have 2 hydrogen and we have 2 oxygen. On the right side, we have 2 hydrogen and we have 1 oxygen. Since I can't make this anything other than 2, I can't change that. So let's start by putting a 2 in front of the H2O. Well, that gives me 4 hydrogens and 2 oxygens. Balances the oxygens. Hydrogens are now out of balance, but if I just add a 2 in front of the H2, that gives me 4 and 2 on both sides. And finally, asking about experimental design. What is the independent variable in this experiment? Well, remember, the independent variable is what you change. Okay, that's what you do. And it says the student changes the mass of baking soda, or soda, depending on where you're from. So, baking soda mass. Okay, that's the independent. The dependent is what you measure. And it says in the problem, measure gas created. And then what is kept constant? What is the variable that's controlled? Vinegar. Volume of vinegar is held constant. So there you go. All right. See you tomorrow.